All right, so let's maybe do one example of what we did yesterday. So let's use our new definition of a derivative. Let's calculate the derivative of that function. Now, what does the derivative mean again? Okay, good. It's the function that's giving us the slope of the curve, meaning the slope of a tangent to the curve. Same thing, right? The slope of the curve for any value of x. Hugely important. Amazing that you can do it so easily. Let's do this. Okay, so we're always going to start off with just the general form of the derivative. For now, we're using limits. Very soon, I'm not going to spend a lot of time doing this limit approach to taking derivatives because we don't do it that way. I'm going to show you we're going to quickly get into learning our derivative rules, which allow us to take a lot of shortcuts. It's a much more quick and efficient way of taking derivatives. But we're going to start off with this limit approach. So what is the limit definition of a derivative as we talked about it yesterday? The limit of what? The difference quotient. Good, yeah. So what is that?
X plus delta x, half of x plus delta x, minus half of x over delta x. That's delta x plus delta.
Okay. So that's, and we remember the picture we drew yesterday, which defined the difference quotient is just the slope of a tangent line. It's really all it is, right? Or slope of a secant line. Right? And you guys understand secant line, we talked about that, right? That just means the line that's connecting the point, the curve at 2 points that allow us to calculate an average rate of change, right? And then our whole process of finding a tangent line was we were just going to let delta x go to 0, so those 2 points that define the secant line just merged into one single point, which became a tangent line, right? Ingenious. Okay, and so now we've just got to get specific. Okay, so our function is f of x. So what is this going to look like? Let's see hands on this. I want everybody to contribute to our little discussion here. So what is f of x plus delta x? What's that going to be? If f of x is x cubed plus 2x minus 1, what's f of x plus delta x? Right up south.
Everywhere where there's x, the function f of x equals x plus delta x.
Exactly. Yeah, good. So we're going to end up with the quantity x plus delta x cubed plus 2 times the quantity x plus delta x minus 1. And then we're going to subtract from that. And I could put that in print or in brackets or something if I wanted to, but I don't really need to, do I? Only purpose it would serve is that we see that that corresponds to f of x plus delta x. But I just made it green, so you can make that connection, right? So what's f of x? Well, we already know. It's just, now I do need parentheses here though, don't I? Because I'm subtracting a quantity. So we get the quantity x cubed plus 2x minus 1, all divided by delta x as delta x goes to 0. Well, what's the algebra look like here? It's a little tedious, but it's not hard. What's it look like? If I try to evaluate this directly, what am I going to get? 0 over 0, right? All the delta x's go away, and I just get f of x minus f of x, and it's 0 over 0, right? So what do I need to do? Liz, you got any ideas? Bunch of stuff. Okay, so we could expand out these binomials, right? If I've got an expression x plus delta x cubed, expand all that out. And that's usually what we're gonna end up doing in these cases, right? We're just gonna simplify everything and then see what cancels. So x plus delta x cubed, what's our pattern? Have we reviewed that stuff? Have we reviewed Pascal's triangle? We did, okay.
We didn't do reveal it. You just told us.
One, two, one, then one.
Yeah, do you know, I'm gonna show you something. I haven't gone through Pascal's triangle with you. I did a couple of years ago, right? Okay, so hopefully you remember that enough then, okay. So remind us then, let's just write this down. I'll write it up here. So x plus delta x cubed then is gonna be x cubed, what's the coefficient that goes there? Remember? 3 x squared delta x to the 1 plus 3x delta x squared plus delta x cubed, right? Okay. And then that just comes from the coefficients we get from Pascal's triangle. I'll review that again. I'm not gonna do it today though. For now, you gotta know, really the only ones you're gonna have to know, ever really, are just gonna be expanding out a cubic binomial and a quadratic binomial. And those are, pretty straightforward. Right. So you should memorize these. If you don't know these, we use these enough that you just wanna have them. A plus b cubed equals a cubed plus 3a squared b plus 3ab squared plus b cubed. And if you have something like x minus 2 squared, well, that's just x plus negative 2, right? So b could be negative if that's a minus sign, but the same rule still holds. Don't remember two of them, just remember the one with the plus sign, and b could be negative. And then you guys all know this one. What's a plus b squared?
A squared plus 2ab plus b squared.
Okay. Okay, so if we expand this out, then we're gonna get, there's our x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 times x plus delta x. I just distribute the 2 there, that's easy, right? Minus 1, and then we'll just distribute the negative sign. Minus x cubed minus 2x plus 1. Well, what do you notice? X cubes cancel. What else? 2 x's cancel. 1's cancel. Everything without a delta x cancels, right? And so we're left with just a few terms. I still can't evaluate this directly, though. What's next? Factor out of delta x. Okay. And then I'm left with, if I factor out a delta x, that term becomes what? What's that guy become? How about this guy? Okay. Somebody else, what's this one? Okay. Somebody different, what's that one? Maisie, what's that one? No, if I factor out a delta x, 2, good. Okay, all divided by delta x. The delta x goes to 0, so now I can cancel my delta x's. There goes the indeterminacy, right? 0 over 0 is taken care of. And now we can just evaluate this. So in the limit, the delta x goes to 0. That term's got a delta x in it, so it goes to 0. That one goes to 0, and so our answer is just 3x squared plus 2, right? Okay, in about a week, you're gonna be able to do that problem right there that I gave you at the beginning. You can tell me the answer within 1 second. Okay, so it's not, there's a rule that we can apply. It's very simple, but we just haven't learned it yet. We're getting there. Okay? So there is another form that we could write our difference quotient in. And it's not like this is a big deal. I don't want to spend too much time on this, but the algebra for doing what we just did is much easier to do if you use the alternate form of the difference quotient. It's not a big deal. They both work. They both essentially say the same thing, but it's kind of cool that you can define this a little differently. So let's go back to our picture. If we've got our function f of x, and let's say this is, we're going to call this some value c, right? So this is the point that we're going to be approaching, right? And we're going to call this other point up here, we'll call this x, and that's going to be a variable. And so the coordinates are just going to be c, f of c, and x, f of x. And we can play the same game we did before with this. We can write the slope of the secant line connecting those 2 points, you know, as a difference quotient, and then we could just take a limit. Now, what's the goal here? If we want to come up with the slope of a tangent line at C, let's say, what's the? You know, this is kind of a dumb way. Our book does this sort of backwards, in my opinion. But I'll do it the way the book does. It's fine. So if we want to come up with the slope of a tangent line at C, what am I going to try to do graphically? What am I going to do? You just kind of picture this in terms of a cartoon. What do I want to do to these 2 points that define the secant line to make a tangent line? Move them closer together, right? We're just going to take a limit as they move together. Well, we could either take the limit as C approaches x or x approaches c. I like it better to say the limit as c approaches x, personally. Our book does it the other way. No big deal. Doesn't matter. It's the same idea. So we could write this then, if we're going to migrate this point back down the curve towards this one to get a tangent line, all we're doing is we're starting off with the slope of the secant line is just, what's the rise over the run here? If I made a slope triangle out of this one, what's the run? X minus c, right? What's the rise? Okay, make sense? Okay. And so our difference quotient then is just f of x minus f of c over x minus c. And if we want to come up with the slope of a tangent line, which is the same thing as the derivative, right? We're just going to take the limit of f of x minus f of c over x minus c as x approaches c, right? The problem with this, the part I don't like about this is then what did you really calculate? You calculated f prime of c. We'd rather calculate f prime of x. So do you see that it really would make more sense? This, and it doesn't make a ton of difference. If we find out, for example, that if we start off with the function, let's just say we start off with the function f of x equals 4x cubed minus 3x squared. Well, if we use this process, what we're going to come up with is f prime of c equals 12c squared minus 6c. So if I want to know what f of x is, what do I have to do? F prime of x, sorry. If f prime of c is 12c squared minus 6c, what's f prime of x? Oh man, this is the Okay, talk amongst yourselves.
Well, time.
It's not work.
No, I enjoy work way more than school, to be honest.
Me too. At least at my work I get like 5 free copies.
Hopefully they have machines for that.
Yeah. Oh, yeah.
I know, I used to
I think
run.
we try to hire more.
It's a real
Guys
shame.
at service because we have like,
Uh,
we have
it's-
indicate, I would, I don't have a trust they would. We have like a million girls.
I did it part-time because
No, I haven't.
let's just sit in a wheelchair.
I would just have an idea.
Just like our rockets.
Caleb
To get around.
is grumpy most of the time. And
That
then
was
Caleb
a- that
does
was
all
a-
of that.
I have,
My sister would be dead ass telling me, she's like, you're an idiot. He doesn't believe her. Like, but she's just young. Yeah. But Jenny, if she tells you that you're stupid, like, you're not like, yeah, she's not, she doesn't care about it.
So they would keep the same code that they used last year. So if we use the alternate form of the difference quotient, if f prime of c is 12c squared minus 6c, f prime of x is just 12x squared minus 12x, right?
Could we go back a step and come to that? You said it's not that clear.
But I'm confused.
Well, that's, I still, what's the question?
No, can we just take a step back and then come back to that point?
Sure. Oh, yeah, so what I just said, you guys, I mean, I just used the trick. I'm gonna teach you guys soon. And you might even be able to see what it is. So I found out the derivative of f of x is just 12x squared minus 6x. And so f prime of c would just be 12c squared minus 6c, right? But then, if we're using this alternate form of the difference quotient, the way it's presented in our textbook, it presents it in terms of c, so then if you want to write it in terms of x, you just swap the c's out for x's. Okay, so, which is kind of backwards in my opinion. I think it would have been better to just define the difference quotient where this was the x and this was the c, and we took the limit as x approached c. Does that make sense? Okay, in fact, let's just do it that way. So instead of writing it this way, we're going to write the alternate form of the difference quotient, f prime of x, as the limit of f of x minus f of c over x minus c as c approaches x. Way better. Okay? Then we end up with an answer in terms of x without having to, right? See the point? Minor point, but it's just a better way to do it.
Wouldn't it be f of c minus? Yeah. Yeah, you just wrote it. I wrote it the same way.
You're right. Everything's the same about it.
Just.
Oh, I see what you're saying. Yeah, okay, f of c minus, yeah, it's, right, so what we would be doing is we would just be having an approach from this side, I guess, instead of, we would leave it as x and c.
Oh,
Right. But all this, how you draw the picture doesn't make any difference, because you can approach from either side, right? And I think that's probably why they did it the way they did it, is so that x could be on the right and the c could be on the left, and you could subtract x minus c instead of c minus x. But why don't we just, we don't have to do that. This stuff is all,
So it doesn't really matter which, limit which comes before the other, as long as one's approaching one, as long as you're.
exactly. So we could make that x and this one c, but then just drag this one towards this one. Doesn't make a difference, right? You can drag the points from either direction. But you see the point, though, that it's easier to let C approach X than let X approach C, because then you don't end up with F prime of C for your answer. You want F prime of X, right? Either way, it's not a big deal, because if you get F prime of C, well, just make it F prime of X. Trade the C's for X's. We don't use this one very much anyway, right? Okay, but we are going to use it now, because the one thing I want to at least start doing, and we're probably not going to finish this, but I want to look at the question of where can you take derivatives. I'm not going to prove this to you, but does it make sense for now? And if I have time later, I'll prove this to you. But the definition of the derivative implicitly relies on limits, right? So doesn't it make sense that any place where the limit doesn't exist, the derivative also would not exist? Okay? That's true. If the limit doesn't exist, then the derivative of the function wouldn't exist there. Okay? So what we're going to do is we're just going to look for some places where, or excuse me, the limit, I said that backwards. Let me say that again. Any place where the function is discontinuous, the limit would fail to exist and the derivative would fail to exist. Okay? And so one thing we know is that if the function is discontinuous, you can't define the derivative, which makes sense graphically. Okay, like if I'm graphing a function, and think what the slope is. The slope is just the slope of the curve is the slope of a tangent. Well, how could you define a tangent line to the curve if my curve did something like this? How could you define a slope of a tangent line at C, let's say, if there's a break in the function there? Right?
Yeah.
Can't do it, can you? Right? Does that make sense? I mean, it's how could you approach from the left to take you can't do it, right? You also couldn't do it if you had a function that had a hole, and that makes sense because the function isn't even defined there. So how could you find a derivative where the function isn't even defined? You can't even have a point of tangency there, right? Okay, but there are some places. There's some tricky places. There's some places where the function is continuous, but you still can't have a derivative. And here's an example. Let's take the function, let's just do f of x equals the absolute value of x minus 2. And let's look at the point 2. Okay, let's try to calculate what's the derivative of this function when x equals 2. So how could we do this?
Is that the point zero with the?
Yeah.
Okay.
Yeah.
Give up the
So it's an absolute value function. What do we always do with absolute value functions? We got to write it as a piecewise function before we can do any algebra on it, right? So we'll write that as, it's either going to be x minus 2 when that's positive. So what values of x would that be when x is? X minus 2 is greater than 0 when x is what? Okay, so there's one piece. It's going to equal the opposite of that, so negative x plus 2 whenever x is less than 2, right? And it's going to equal 0 when x equals 2. Okay, everybody good with that? Okay, so if we want to calculate a derivative then, what's the derivative of x minus 2? Now just think about this. This is a line. We don't have to even do any math here. What's the slope of that line?
1.
1. So if I have a line with a slope of 1, what's going to be the tangent, the slope of the tangent line of every point on that line? 1, right? The tangent line is the line in that case, isn't it? If it's a line, right? So would everybody agree that here, even if we did the math with the limits, we'll just avoid it because we don't really need to. We could. We're going to get a slope of 1 whenever x is greater than 2. What's going to be the slope of a line with a slope of negative 1? What's the slope of a tangent? Negative 1, right? If that's the line, then that's also the tangent line. Right? Does everybody get that? If I draw a picture out here at 2, this is what that's what my curve looks like, right? My absolute value function. So if I'm up here someplace, If I draw a tangent to the line there, well, the tangent is the line. If I draw a tangent over here, well, the tangent is the line. So they just have the same slope as the line, okay? So here I get -1 whenever x is less than 2. What's the problem? At 0, what would the slope be? I'm not getting, it's not working, is it, right? Because I'm getting different slopes from different directions, right? See what I'm saying? And so we can't define a slope there because ants walking from different directions would anticipate different slopes. We have these new highly evolved ants now, in addition to knowing their x and y coordinates on the xy plane, they also can sense their slope. Their slope sensors would tell them different things as they walk towards that point. And so this is a place, one of the places where functions don't have derivatives. Derivatives are not defined at sharp corners. Okay? I really wish we had a little more time.
Okay.
Next week.
With slope sensors.
I'll just cancel my next class. Let's just keep going with this. What do you say?
But my next class is really.
My next class is
Yeah.
orchestra and